All right, so here we're in 11.2 on second derivative and graphs. So here we're going to be using concavity as a graphing tool, finding inflection points, analyzing graphs, curve sketching, and point of diminishing returns. All right, so here we use the term concave upward to describe a graph that opens upward and concave downward to describe a graph that opens downward. Thus, the graph in figure A here is concave upward, because if we look here, it's going, if we look up, it's concave up. So the upside here is concave up. And then in figure B here, it's concave down because we have everything going on the bottom side here. So finding a mathematical formulation on concavity is going to help us sketch and analyze graphs. So again, concave and up and concave down here. Now we examine the slopes of f and g at various points on the graph and make two observations about each graph. And for one, looking at the graph in figure A, we see that the derivative f prime of x, the slope of the tangent line, is increasing and that the graph lies above each tangent line. So if we look at on this one, as we go, we take the tangent line and it's below the graph. But as we go up higher and higher, our slope is getting bigger and bigger. And if we go this way, our slope's going to get closer and closer to zero, but then it keeps going up higher and higher. Now, on the other one, B, we see for the g of x, the derivative is decreasing. So here, if we start here, we have a pretty high slope. Then as we go further and further and further up, our slopes are getting smaller and smaller. And we also notice our graph lies below the tangent line. And so this one is x squared, this one is the square root of x. So, that doesn't really matter as far as what the functions is, but we see that, how the slope is and also where the graph lies in relation to our derivative. So for concavity, the graph of a function is concave upward on the interval from a to b if the derivative is increasing on the interval a to b, and the concave downward on the interval a to b if the derivative is decreasing on a to b. Okay, again, here we notice it's increasing, so that means it must be concave up. Here it's decreasing, so it must be concave down. Okay, so we use the derivative to determine when a function is increasing or decreasing, and we will now determine when the derivative is increasing or decreasing by taking the derivative of the derivative. Okay, so the derivative of the derivative is now called the second derivative of the function. And so that's kind of what we show here. So the second derivative for y equals f of x, the second derivative of f provided that it exists, I should say, is f double prime. So before we were just taking the first derivative, now we're doing the second derivative. So the double here is the derivative of the first derivative. And other notations for the second derivative are d2y over dx squared and y double prime. So those are different ways to represent the second derivative. Now, for concavity in summary, for the interval from a to b, if f double prime is greater than 0, then f is concave up. And if f double prime is less than 0, then it is concave down. So here, again, our double prime, if it's positive, then f prime is increasing and it's concave upward. And so it looks something like this, or, we just have part of a circle or part of a x squared. And if the f double prime is negative, it's decreasing the derivative, and so therefore it's concave downward. Okay, so again, however, it's split apart. All right, so let's stop there and then we'll come back with an example.